Today, we're going to break down the magic behind automation. We're talking about the core components that let machines do all sorts of complex, real-world things, from a simple conveyor belt all the way up to a crazy, sophisticated robotic arm. So you ready to take a look under the hood? Let's get into it. Have you ever wondered about that? I mean, how does a machine, just a chunk of metal and wires, know exactly when to start or how long to run a process, or maybe how many things to put in a box before it stops? Well, the answer is a powerful little box that acts as the brain for pretty much all of industrial automation. So here's our game plan. First, we'll meet the brain itself. Then we'll see how it talks and listens using simple and not so simple signals. After that, we'll check out how it keeps track of time and how it counts things. Then we'll peek into the programmer's toolkit. And finally, we'll see how all of these pieces snap together to create real automation. All right, time to meet the star of the show, the Programmable Logic Controller, or as pretty much everyone calls it, the PLC. So what is a PLC? Well, think of it as a super tough, specialized computer that's built to survive in a rough and tumble factory environment. Its job is actually pretty simple, but it's absolutely critical. It just runs in a continuous loop over and over again, super fast. First, it reads all of its inputs, sensors, buttons, switches. Then it runs the program that a person wrote for it. And finally, it sends out commands to its outputs, things like motors, lights, and valves. Read, think, do. That's it, over and over again. Let's start with the most basic language that a PLC speaks. This is the simple black and white world of digital I/O. Just think of a regular light switch in your house. It's either on or it's off. There's nothing in between, right? That's a digital signal. An input could be a button that's either pushed or not pushed. An output could be a motor that's either running or stopped. It's the fundamental yes or no language of the entire automated world. Okay. But what if on or off just isn't enough information? What if you need to know how hot something is or how fast a motor is spinning? For that, we got to go beyond the simple binary world and check out analog I/O. This slide just lays it out so perfectly. Digital is the light switch, right? On or off. But analog is the dimmer switch. It can be anywhere from 0 to 100%. Digital tells you, yep, the button is pressed. Analog tells you the temperature is exactly 72.3 degrees. It gives us this beautiful, continuous range of information, and that is absolutely key for any kind of precise control. So an analog input is basically a translator. It takes a real-world measurement, like the temperature from a device called a thermocouple, and it turns that physical property into a number that the PLC can actually understand and work with. So instead of just knowing hot or cold, the PLC knows the exact temperature. And you guessed it, this works in reverse too. With an analog output, the PLC can take a number from inside its program, let's say the number 65, and it translates that back into a specific voltage or current. This lets it tell a motor not just to turn on, but to run at exactly 65% of its top speed. This kind of fine-tuned control is what makes really sophisticated automation possible. Okay, so our PLC can now understand all these different signals. But for most jobs, that's not enough. It also needs a sense of time, and it needs the ability to count. And this is where two incredibly important tools come in: timers and counters. This quote really sets the stage. In any kind of automated production, timing is everything. You have to feed a part in at just the right second, or maybe you need to let a process run for a very specific amount of time. Let's look at a really practical example. Here's a classic safety and quality control problem. You can't just fire up the grinder and the coolant at the same instant. You'll ruin the part or the tool. The coolant has to come first. So how do we get the PLC to wait? The solution is a timer. When the whole process starts, the PLC immediately turns on the coolant. But at the exact same moment, it starts what's called an on-delay timer. This type of timer basically waits for a set amount of time after it gets the go signal. So the PLC just waits, and only after that timer hits 8 seconds does it finally turn on the grinder. There are other types too, like off-delay timers, that keep something running for a bit after you turn it off. It's a simple, elegant, and safe way to control a sequence. All right, now for a totally different kind of problem. This one isn't about how long something runs, it's about how many times it runs. Let's say we only want to make a batch of 10 items. We can't just let the machine run forever, right? And the solution here is a counter. It's so simple. Every single time a sensor sees a part go by, it sends a little signal to the PLC, and the PLC just adds 1 to its count. This is called an up counter. So the PLC's program is constantly asking, are we at 10 yet? Are we at 10 yet? As soon as the count hits 10, bam, the program shuts the whole thing down. And of course, there are also down counters that count from 10 to 0, and even up/down counters that can do both. So these timers and counters we've been talking about, they're not things you have to build from scratch every time. They're actually pre-built tools that are part of a programmer's toolkit, and these tools are called function blocks. Think of these function blocks like pre-made Lego pieces that each do one specific job really, really well. You've got your timers and counters, obviously, but you've also got blocks for doing math, for comparing numbers, for moving data around in memory, and for basic logic. A programmer builds a huge, complex program by snapping these simple, powerful little blocks together. And this is where it gets really cool. You can see here how you chain these blocks together to create a whole sequence. This example shows a robotic gripper. It's programmed using something called ladder logic, which is a visual language that kind of looks like an electrical diagram. It makes it easier for technicians to understand. Each step or rung of the ladder uses a function block, maybe a timer for a little delay, then an output block to make a cylinder move. All these simple blocks working together create a complete, useful action. And that really brings us to the big picture. We've seen how a PLC senses the world, how it understands time and numbers, and the tools it uses to think. So now let's put it all together. It really is that elegant. Some of the most complicated automated systems you can possibly imagine are all built from these same simple, fundamental pieces. A basic on or off signal, a precise analog value, a timed delay, a simple count. By combining these building blocks in clever ways, we create the powerful logic that literally runs the modern world. So there you have it, a peek inside the brain of automation. It isn't magic, it's just a really logical system of inputs, outputs, and a powerful set of programmable tools. Which leaves just one final question for you. Now that you know what the building blocks are, what would you automate? Thanks for joining me on this one. I'm excited to think about what you'll create.